In this video, we're going to apply the comparison theorem for improper integrals to show whether the integral from 1 to infinity 1 minus e to the minus x squared divided by x to the fourth integrated with respect to x, whether it converges or diverges. We're going to apply the comparison theorem for improper integrals to answer this question. Let's start with the fact that x is bigger than 1. We know that because we're integrating from 1 to infinity. Let's square both sides and we get x squared is larger than 1. Let's multiply by negative 1 both sides. We get minus x squared is less than minus 1. The sign switches. Now let's exponentiate both sides and we get e to the minus x squared is less than e to the minus 1. We also know that e to the minus x squared is larger than 0. So that implies that e to the minus x squared is less than 1 over e and is larger than 0. Now let's multiply everything by negative 1. We get minus e to the minus x squared. Switch the sign. That's larger than negative 1 over e and less than 0. Now let's add 1 to everything. So we get 1 larger than 1 minus e to the negative x squared larger than 1 minus 1 over e. And we can rewrite this as 1 minus e to the minus x squared is less than 1 larger than 1 minus 1 over e. Now let's divide everything by x to the fourth. So we have 1 minus e to the negative x squared is less than 1 larger than 0. Actually, it's larger than 1 minus 1 over e, which is larger than 0. And we're going to divide everything by x to the fourth. Why do we do that? It's because we want to build up this integrand. That's the reason. So we're going to divide by x to the fourth, divide by x to the fourth, divide by x to the fourth. So what we have shown is we've shown that 1 minus e to the negative x squared divided by x to the fourth is less than 1 over x to the fourth and is larger than 0. Alright, so what we have is, let me repeat that, 1 minus e to the negative x squared divided by x to the fourth, which is the integrand of the improper integral, so we have a bound for it, is less than 1 over x to the fourth and larger than 0. Now let's integrate from 1 to infinity, and we get integral from 1 to infinity 1 minus e to the negative x squared over x to the fourth dx is less than integral from 1 to infinity 1 over x to the fourth dx. But you will notice something. This is actually an improper integral. It's a p integral with p is equal to 4. So what we have shown is that the integral in question is less than something that converges, a convergent p integral. Let's repeat that. Since the integral from 1 to infinity 1 over x to the fourth dx is a convergent p integral with p is equal to 4, the integral that we're after, integral from 1 to infinity 1 minus e to the minus x squared over x to the fourth dx, converges, and it converges because of the comparison test for improper integrals. We made the integral that we wanted to examine its convergence, we made it less than a convergent improper integral, a p integral with p is equal to 4. So the integral in question, this integral from 1 to infinity 1 minus e to the minus x squared divided by x to the fourth dx, this integral converges because it's less than a convergent improper integral. Alright, let's look at another question. So here we have, does the integral from 1 to infinity 2 plus sine x divided by x squared dx, does it converge or diverge? Let's apply the comparison test for improper integrals. We'll start by building up an upper bound for the integrand 2 plus sine x over x squared. So let's start with sine x. we know that sine x is between 1 and -1. Now, we add 2 to everything. We get 2 plus sine x is less than 2 plus 1, larger than -1 plus 2. And what do we get? Well, we get 2 plus sine x is less than 3, and larger than 2 minus 1 is 1. So 2 plus sine x, the numerator of the integrand we have shown, is less than or equal to 3, larger or equal to 1. What is the next step? Well, here we have 2 plus sine x divided by x squared. We want to build up the integrand. So divided by x squared. Divide by x squared. Divide by x squared. Divide by x squared. So now let's integrate. We have integral from 1 to infinity, 1 over x squared dx, less than or equal to integral from 1 to infinity, 2 plus sine x, divided by x squared dx, less than or equal to integral from 1 to infinity, 3 over x squared dx. 3 is a constant, passes through the integral, so we can just write this as 3 times integral from 1 to infinity, 1 over x squared dx. Alright, so what we have shown is that the integral 2 plus sine x divided by x squared from 1 to infinity is less than 3 times the integral 1 to infinity 1 over x squared dx. It's important to note that this is a p integral with p equal to 2. That means that since 1 over x squared, integral from 1 to infinity 1 over x squared dx, is a convergent p integral with p is equal to 2, the integral in question, the integral from 1 to infinity 2 plus sine x dx, 2 plus sine x divided by x squared dx converges by the comparison test for improper integrals. The big picture is this. The integral that we were after, the integral 1 to infinity 2 plus sine x over x squared dx, is less than a convergent improper integral with p is equal to 2. That means the integral that we're after converges by the comparison test for improper integrals. Alright, let's look at another example. Here we have, does the integral from 3 to infinity 1 over root x times log x dx, does it converge or diverge? Let's start by analyzing the denominator root x log x. You will notice from the graph, it's clear from the graph of root x and log x, that root x is larger than log x for x larger or equal to 1. So we're going to build up an inequality for the integrand, 1 over root x log x, so we can apply comparison test for integrals. Alright, so let's start with the fact that root x is larger than log x for x larger than 1. So definitely root x is larger than log x for x larger or equal to 3. So the denominator root x log x is less than root x times root x, because ln x is less than root x. So what that means is that root x log x is less than x, because root x times root x is just x. Let's reciprocate both sides, and we get 1 over root x log x is larger than 1 over x. So what we have shown is the integral from 3 to infinity 1 over root x log x dx is larger than the integral from 3 to infinity 1 over x dx. What do you notice about this integral? This is a divergent p integral with p is equal to 1. So let's repeat that. Since the integral from 3 to infinity 1 over x dx is a divergent p integral with p is equal to 1, the integral in question, the integral from 3 to infinity 1 over root x log x dx, diverges by the comparison test for improper integrals. So the big picture is that the integral from 3 to infinity, 1 over root x log x dx, is larger than a divergent improper integral. Therefore, it also diverges. All right, thanks.